Hey guys, Aaron with Grandpa Ray Outdoors. Wanted to take some time today. I had this soil pit dug for a couple of events that I did this week. And I wanted to take this opportunity to do some education here. Kind of break down the soils, break down how the nutrients are moved throughout the soil, and make it simpler to understand. A lot of times John and I are spreading words out there that we're not given the basic understanding of what that is. And I want to break it down to a level that everyone can kind of understand what we're talking about and just get an understanding of how the soil system works. One of the first things that we got to realize is that all soil at one time was a rock. And a rock is just a conglomeration of minerals that have been either molten lava that's cooled off or pushed together to form that rock. And then over many different things such as weathering, erosion, and there's actually bacteria out there that are called lithotropes that eat rock, that take small bites. It gets broken down into three major particle sizes, and that is sand, silt, and clay. And then you can have a combination of the sand, silt, and clay, and then that gives you other soil types that fit within that spectrum then. So when we look at soil, the content of it, we know we've got the minerals because it was all rock at one time. So minerals make up 45% of most soils, and then you got 25% that's air. There's air infiltration that's going down into the soil, 25% water, and then there's about 2% of what's called necromass. And when you think of necromass, it's just dead living things that were once alive. You've got plant material, you've got animal material, you got fungus, you got bacteria, animal manure, all that litter that's sitting on top of the soil. And then 1% of the soil is living organisms, whether it be insects, fungal, hyphae, bacteria, protozoa, stuff that's actually living inside that soil. So what we're going to do today is we're going to do a quick run through of the horizons. When you look at soil, soil is broken up into horizons. We're going to spend a lot more time on the O horizon today because that's what's going to lead us down that path of talking about the stuff that John and I talk about all the time with plant nutrition. So when looking at the layers in soil, the top layer before you hit any sand, silt, or clay is called the O horizon. With the O horizon, the O, you can use that to think of organic matter. So the O horizon is plants, dead animals, manure, decomposing litter. That's the O horizon. There are bacteria and fungi that live in that layer. There's a lot of small insects, they call them shredders, that are eating that material and decomposing it. So that layer is going to be really important for us to come back to when we talk about the rest of the horizons that we're going to go to. So when most of us think of soil, we think of topsoil. And below the O horizon, you get into the A horizon. So this darker area is the A horizon that takes you down to about here. And you can see we've got some root growth coming out of the A horizon. So what gives that A horizon that dark color is everything that's happening up in this O horizon. So as this stuff is decomposing, as it's getting broken down, it's leaching into the soil and giving it this nice dark color. Below that A horizon, you've got your B horizon, and that's basically your parent material, or what's underneath, that has been broken down a little bit farther than the parent material. So in the B horizon here, we can still see some coloration changes. So we know that we've got some leaching of some of that broken down organic matter coming down into here. So it is got some nutrients available from the broken down O layer also. In this pit, for example, we also see some modeling. And what that is that's actually showing where the water table at one time was, and it was bringing the iron up. And then as the water would recede back down, it would leave them iron modeling spots in the soil. So if you think, if you've heard of a perk test, if you've ever had a perk test done, that's what they're looking for when they do a perk test, to see if you can put a conventional septic in, or if you need to do a mound septic. So we've got the O horizon, the A horizon, and then we got the B horizon. And because of the water level coming up, there's actual different levels of the B horizon. Below that, you're gonna have the C horizon, which is gonna be larger particles of the parent material. And again, down there, there's still bacteria that are eating that parent material, eating that bedrock, and transforming it into the smaller particle sizes. So taking all the horizons into account, we know we've got this A horizon that has this really dark color to it, and that's what we really want to focus on today. So as organic material breaks down, it's called humus. And humus is one of the most important things that we have to make sure that we have nutrients available for our plants. So as this material, dead animals, dead insects, dead plant material is breaking down, during the process it goes through several different changes and molecular changes, and it breaks down smaller, and it breaks down smaller, and it breaks down smaller. When it gets to the very bottom, to where it is now as far as that can possibly be broken down, then it's got what's called humic acids. The humic acids are very important. And again, it all starts with the top layer of stuff getting broken down. Now, there are organisms that are dying in here that are continuing to get broken down, and down there and farther on too. But that is what's really important to us as food plotters or gardeners or agriculturists, is making sure we have that O layer, providing that material of decomposition, which is getting that humus that is then broken down. So when the humus gets to the final stage, it can no longer break down any farther. It's broken down into three different things: humic acid, fulvic acid, and humin. We're going to really focus on the humic acids today, because the humic acids are really important to plant health. And the reason that the humic acids is the last transformation that happens to that molecular structure is it releases the positively charged hydrogen ions. So what you're left with then is the simplest possible structure that's negatively charged. Now, for us, that's a good thing, because if you have something in the soil that's negatively charged, we have our minerals like iron, manganese, copper, zinc, they're all positively charged. So what happens is a process called chelating. We've talked about chelating before. I'm not sure we've ever really broken it down to explain it. And the best way to explain it is chelating. The word chelate comes from a Greek word called chile, and chile means lobster claw. So you picture this molecular structure that's got these lobster claws on it, and they're negatively charged. So you've got a negatively charged lobster claw, and you've got a positive zinc or copper mineral that comes along, and they're going to bind together. So now you fill this humic acid with all these positively charged beneficial minerals, and it holds them in the soil so that if you get large rain events, they don't just wash through. This is sandy ground. This is the specific soil mapping. They call it a Watoma loamy sand, which means it's mostly sand with a little bit of loam. For us that are in sand ground, this is very important, because sand is not positively charged. If you've got a lot of clay soil, you've got a lot of positive charge in the clay, which will hold some of those minerals in there. If you've got sand, it doesn't have that positive charge. So you get a lot of rain events, it's going to wash all your minerals through. But if we can have the old horizon praise and the humus that's breaking down into humic acids, now our humic acids are in the soil, they're negatively charged. So as those minerals that are positively charged are in the soil, they're grabbing hold of them, and then that structure can't be washed through, so it holds it there. So that brings us to, okay, how do we get that to the plant then? Well, a plant's root is also negatively charged, and the negative charge of the plant root is actually stronger than the charge on the humic acids. So that humic acid is going to be pulled to the plant root because of the stronger charge that it has there. So that humic acid goes through the soil, comes to the plant root. Now all these positively charged minerals are going to jump because the charge is stronger over here. Then all of a sudden this humic acid doesn't have them positive charges anymore. And it's gonna it's gonna be pulled back towards the minerals again. It's gonna load up, then it's gonna be brought back to the plant root, and they're gonna exchange. So that's one very important thing that humic acids do for us. The other thing that humic acids do is that they feed the microbes in the soil. And microbes are a huge benefit to also having the nutrients in the soil, because what the microbes do is they also eat these minerals. The minerals that are in the soil are not plant usable form. A root can't just drop a root down and find a molecule of iron and uptake it, because it's not in a plant usable form. But there are microbes in the soil that are eating that are eating each other. So if a bacteria eats the mineral, and then something comes along and eats that, and then it expels it, we call it the poop loop, then that will then make that nutrient plant usable. So two major ways to get nutrients in the soil is with the old horizon breaking down into humus, not hummus, humus, leaching down into the soil, the microbes transforming that into plant available food and coming back. So when you've heard John and I talk about the CEC, that is the cation exchange capacity of your soil. Cation exchange, just think chelate, remember the lobster claw. We have our humic acid that is grabbing onto those positive mineral ions or molecules. So all of a sudden we've got chelated minerals that are then brought to the plant root takes them off, it goes back out. So that's the importance of humic acids to us that we talk about. And also we're going to explore a little bit more into biology and some seminars that I'll do later to talk about more into the process of how the biology can produce plant usable minerals. I hope this shed a little light for you guys today. I was happy I was able to use the pit to kind of show the horizons for you guys and give you an idea of some of the stuff that we've got going on. But we'll have more seminars coming up. Aaron with Grandpa Ray's. Thanks for watching.